Hi everyone. So this will be a bit of a different presentation because I will not really like present a result of my work or like try to advertise what I do and so forth. But it's more like my discussion, like some notes about my like a bit of research and a couple of things that came out in the last ISMRM and some connections between them. So I hope to create some discussion and like see where this will end up in the future. So it's a bit like maybe all over the place, but we'll see. Okay, so it's about spatial phase derivatives and where is this coming from? Well, I'm talking about spatial phase derivatives because there was this kind of popular ISMRM abstract that came out, and we discussed in this meeting a month ago from Raya et al. And that was basically proposing a new method that is blood insensitive and like conductivity sensitive or somehow like conductivity measuring. And basically they were showing some striking results in which they, for instance, here claim that you can see even white matter activity, I mean, whatever that means, for the left and right index finger stimulation. I mean, if this is true, this is very big news, and this might have lots of like implications for what we do with regards to fMRI and how we detect the brain activity and so forth. But then also a month ago, when Tyler was talking about this abstract, she brought up the uh, equation that they use to compute this thing that they measure. And basically that is, and we don't need to go into too much detail, but this is essentially the Laplacian of the phase. So they are recording fMRI time series. They are looking at the phase component, not magnitude, the one that we look at most of the time. And they compute the Laplacian of it. I will explain a bit more in detail what is Laplacian in this context. And then they scale it with some number, but this we don't need to care too much because at the end, they are doing like modeling statistics GLM on this Laplacian of the phase time series. And then this somehow gives you these nice, even white matter activity. And this was particularly striking because they also showed this result repeating across different subjects. And you can really see like either left or the right white matter tracks that are connecting the fingers to the motor cortex or the sensory cortex is lighting up. So if it's true, this is big news. Okay, so first, just to keep everyone together following what's going on, uh, like briefly some basics, and I will have lots of simplifications, but hopefully this is the right level. So MRI signal is complex valued. We are most of the time looking at the magnitude part of the resulting brain image, but there is also, for instance, here you can see the phase component. Okay, now, so just to, this is also a little bit like more hands-on. Just to give you some feeling of this data, you can see the following. For instance, here I am plotting some data set from Renzo that I have acquired. This is some motor cortex data, finger tapping experiment, time series. And now we can play it as a movie. Like this is without any pre-processing, nothing. Like it's just coming out from the scan. And you can see that it's moving around, going darker, lighter, and so forth. This is the usual fMRI data that we talk about. And this is the phase component of it. And you can hopefully see that it looks somehow more complicated and maybe confusing, maybe worse in certain ways. But basically the essential thing here is that the phase component is a circular measurement, which means that it is scaled between 0 to 2 pi or minus pi to pi, or as it comes from the Siemens scanners, most of the time minus 4096 to plus 4096. And that happens to be integer 13 range somehow. Someone coded it in that way. And it's a circular measurement. So if you switch to a color map that is circular as well, you do not see that strong edge anymore because hopefully you can see that like from 0 degree to 359 degrees, the difference is not 359, but it's just like 2 degrees, right? It's a circular measurement. Okay, so hopefully this puts an image into your mind. So now let's talk about what do we mean by saying spatial derivatives? So spatial derivatives are in general very useful in image processing context or image analysis context. For instance, here you can see that we start from a magnitude image and we can compute the first derivative of it, which means that you compute the rate of change over three cardinal axes of the image, that is x, y, z, I denoted here. I mean, this is like, if it's your first time seeing these things, I know that it's not so easy to just grasp what these are, but basically you look at a voxel, you look at the voxel right next to it, and you compute the difference between them. That's a measure of that's a first spatial derivative. You can do like what is upper, what is lower, and so forth in more complicated ways to compute these spatial derivatives. This is just the first spatial derivative, though. So for MS, in another words, like there are many words to talk about these concepts. Like one concept is that you start from a scalar field and you derive a vector field from it. You measure like rate of change in three different dimensions. So basically like a voxel starting from a magnitude image becomes having a vector valued voxel. It has three values written inside. So, okay, now I'm moving towards Laplacian to explain what is Laplacian in this image processing context. So to arrive to Laplacian, you need to compute the second spatial derivative as well, which means that you need to compute the rate of change among x, y, z on the gradients themselves. So which basically turns the vector field into a matrix field or a tensor field. Like this means that each voxel is now represented by 9 values eventually. So this is a tensor. Some people call it a structure tensor. In other contexts, this is called the second moment matrix. In other contexts, this is called the Hessian of the image or Hessian of whatever. There are many names for it, and this 3x3 structure is a very useful structure. If any of you used, for instance, Frangi filters in the past, or like diffusion filters, structure tensor filters, they all leverage this structure. So 9 values per voxel derived from a singular scalar valued image. So the Laplacian of this image is basically a subpart of this structure tensor. When you sum the diagonal, so gradient x over x, y over y, and z over z, you basically compute spatial Laplacian. That's it, like as simple as that. So what does it mean and how to interpret the Laplacian and so forth? Hopefully it will become a bit more clear. So at some point we will connect it to fMRI. So now let's switch to phase. Well, we start from the magnitude image, that was easy and so forth. With the phase, we need to take into account the circular nature of our measurements. As we discussed, like if you measure in one voxel 1 degree, and in the next voxel, if you measure like 358 degrees, the difference is not 357. It's smaller, right? Because it's a circular measure, it wraps around. If you account for this circular nature, you can straightforwardly derive the first spatial derivative. This is like a circular difference operation. And similarly, you do the same. You derive the second spatial derivative. There is one useful property when you do this on a circular measurement. Like this becomes to have a natural 0 point. And this like gradient or the derivative measurement becomes between -pi to pi, in other words. And here in the second spatial derivative, again, you can derive the Laplacian of it. And as far as I understand from that ISMRM abstract and the papers that they cited from their group, like it's not so easy to understand all the details, because I think that all the details are not out there yet with regards to what they did in the ISMRM abstract. Like, I mean, the code and so forth, like very specifically. I think they are basically computing this, like they are computing the Laplacian in the phase data, and from here they are deriving an image that is this one. So now this was interesting because at the same time and in the same ISMRM, I had another abstract that was showing the benefits of something I call phase jolt. And phase jolt is again related to the second spatial derivative of the phase, this structure tensor field. And instead of computing the Laplacian for a couple of reasons in the anatomical imaging context, I was computing this thing called phase jolt. I made the name up because I didn't encounter anything that is called like that. And that is simply the L1 norm of the matrix, voxel-wise. And L1 norm means that you just go to each voxel, you take the absolute value, you sum them, and divide by the total number of voxels, which is 9 here, because every voxel has a 9 value measured in the second spatial derivative. So okay, then like actually like with Tyler, Renzo, and Peter and so forth talking about it, I made the connection that, oh, these things are actually similar. So let's maybe try to think about it and let's see how they work out in the fMRI context, this second spatial derivative of the phase and what it means and so forth. So, okay, just a side note, because I do believe that there is a value to consider phase jolt over phase Laplacian from a geometric and just like voxel statistics point of view. And it is this one. Here I am showing you let's say high SNR 0.35 millimeter isotropic anatomical image that is acquired at 70. Like the details are not so important. But here I am just showing you the signal, like population characteristics over a voxel area, sorry, like air area and the white matter area, just like pure tissue, to represent like very low SNR and very high SNR regions of the image. And when we look at the magnitude, just distributions over this, you can see that the magnitude, as expected, is very close to 0, right? Because magnitude measurements cannot be below 0. They have to be positive real numbers. And maybe some of you realize that this follows a Ritchian distribution, because when you compute the magnitude of a complex data, as we do in MRI and fMRI, at a low SNR regime, it's not a Gaussian, the resulting distribution. At the high signal regime, it basically approximates a Gaussian. You see, and it's of course away from 0. So this is all straightforward, I guess. Now let's have a look what's going on in the phase, because phase is rather different compared to magnitude. When you look at the air voxels, you see that the distribution of the voxels there doesn't follow Ritchian or Gaussian. It follows a uniform distribution, actually. This is like, it's like a straightforward geometric fact, and when you think about it, you see it. But I hope you can agree that this is like something drastically different that happens in the phase data, and maybe we should like keep it in mind when we are operating on the phase data. Again, in the same high signal region, that is white matter here. I cannot easily check the chat and so forth, but if someone checks, like stop me or ask me a question.
I'm keeping track of it. No questions.
Yeah. So in the white matter, you can see that it follows a Gaussian again, but of course, especially in this region, it's a split Gaussian that is actually wrapped. So this is a complete Gaussian if you imagine this x-axis as a circle. Okay, now hopefully this like made some sense. Let's move to phase Laplacian and how things look there. And I'm showing you to kind of clarify what is the difference between this like phase Laplacian and phase jolt I talked about. In the air, the phase Laplacian is zero-centered, and there's a thick distribution. In the signal area, high SNR area, it is zero-centered and it is narrow distribution. Whereas when we switch to phase jolt, it's substantially different. In the air area, it is half pi centered, thick distribution. In the white matter area, high signal area, it is actually close to 0. So I hope that you can see that there is some duality between the magnitude image that we measure at the high SNR, low SNR regions of the image, and how what type of numbers voxels measure there and this, like show between like magnitude and the phase jolt. Whereas in Laplacian, this is like rather different. And I think this has some implications with regards to how we do further statistics and time series and analysis and so forth. I will hopefully come back to that one in the future. So, okay, with regards to just like this phase jolt stuff and what's going on. So there's a clear advantage of looking at the phase jolt to summarize what's going on in the second spatial derivative of the phase data. And that is because there is this like similarity between magnitude and phase jolt. You can straightforwardly average many runs at high resolutions or whatever. And then more you average, the tissue contrast will pop out further and further. For instance, here you can see that I see the subcortex quite nicely, the iron-rich areas kind of popping up in phase jolt. Maybe you can even say that to some degree, you can even distinguish white matter, gray matter, and so forth. Whereas when you look at the phase Laplacian, like for a human, just looking at the image, this is not so easy to understand compared to magnitude or phase jolt images. So there is a pretty big qualitative and quantitative difference between these like summaries of the second spatial derivative of the phase, let's say. So we need to keep this in mind for the future. Okay, then, so just as a side point, like this phase jolt stuff is something that really works, and it works in the anatomical context. I am not like trying to convince you that it's better than Laplacian or something. It's like different, and it works for tissue segmentation purposes. And one strong point of doing that, actually going to the second derivative at all, with the phase images, is that you can see that the susceptibility artifact that kind of pops out further and further as you increase your echo time. Hopefully this is clear when we look at the phase. This like area, like the phase over space is changing in an accelerating acceleration way. So when you look at the second spatial derivative, you kind of nullify to a large extent this like accelerating first derivative, like numerical energy thing. And that by itself has useful properties to do like anatomical tissue.
Ömer, I have a question.
Yes.
Maybe why is this ring in the middle here happening in the face?
No, it is just a large susceptibility artifact. Like it happens in every MRI data
Is it
because
because
of
of the sinuses, or this is the location?
Yeah.
Okay.
Yeah, it's the sinus thing. It happens cortex as well because of the ear cavities.
Oh yeah. Okay. Thanks.
Yeah, it's like due to, just to summarize, it's due to the large susceptibility, magnetic field susceptibility differences between like these large tissues like air and brain, and phases kind of messed up the. Okay. So, and you can have a look at the details and recognize that, oh, like I see a big vein here, and I see it also popping up in the phase jump and phase jolt. Phase jump is like a first spatial derivative related thing. And just to say that it has some anatomical useful properties. Okay, now coming to fMRI, finally, hopefully. Here I am showing you just some time series from a pretty standard like ultra high field, not even so high resolution, like 1.8 millimeter isotropic resolution data set. This is like 2D gradient echo EPI, pretty, I would say, standard stuff from CMRR, thanks to Kendrick. And just in case if you didn't look at the phase time series in the past, like it looks like this. This is unpreprocessed data. So no head motion correction, no like high pass filter, nothing, as it comes from the scanner. So here is the magnitude, here is the phase. You can see that the phase seem to fluctuate a lot. But again, remember that this is just because we are plotting the circular measurements in a non-circular color map. So it kind of emphasizes the edges that like 0 degrees switches to the other way around. And what it means to compute the Laplacian of the like volume-wise Laplacian of the time series. So, and I'm, if I understand correctly, like basically this is what they are in a way looking at in this ISMRM abstract when they are talking about this like new method. They compute essentially the Laplacian of the phase, that is this guy, and they scale the Laplacian with different numbers based on the tissue like modalities, like white matter versus gray matter are scaled differently and so forth. Hopefully I'm correct on this, like if I understand their previous paper correctly. And here, just to give you an example, this would be the phase jolt of the time series. And also notice that these like 2D acquisition related artifacts are really visible in the phase. And of course, when you compute spatial derivatives of the phase, you need to make sure that you are not kind of mixing slices if you have a 2D acquisition if you are recurring with like 3D like API, of course, you might want to do it fully 3D and not slice by slice and so forth. But just to give you some, like put some image in your mind's eye about these things. So, okay, why should we care about it other than these like complicated looking images? Well, there is clear activity in these images. And here I selected the data from Renzo, that is finger tapping, very strong task. I believe this is an average of multiple runs. So it's like really nice high SNR data. And I'm selecting really like a large vein, that is large pile vein, like on purpose. So for those who are unfamiliar, this is kind of the CSF area. This is like one part of the gray matter. So gray matter here, I believe this is the motor cortex up here and some of the sensory cortex down there. And Renzo can correct me if I'm saying incorrectly.
It's all correct. I think it's a single run, very thick voxel. So.
Oh, okay. This is a single one, a single run. Yeah, and the resolution is at 0.75 by 0.75 by 1.25 millimeter. So it's anisotropic fMRI voxels. And here you can see that without doing any statistics and not even pre-processing, right? This is like not pre-processed data. I can just detect finger tapping activity. In red, you see the finger tapping events. Like, okay, there's clear like brain activity detected. And I say brain activity, and I don't mean like neuronal activity, just like putting neurons, vessels, everything together. When I compute the phase Laplacian, I don't have the phase results here, by the way, because I didn't have time to like process the phase data by itself. So I just skip it for now in the context of this ISMRM abstract. In the phase Laplacian data, again, the same voxel, maybe it is not so clear, but you can still see this like up-down movement, right? In the response curves. This is a single voxel, by the way. Like I am taking a single voxel looking at the time series. And here I am doing the same, but with the phase jolt, this other summary of the second spatial derivative. And hopefully you can see that, for instance, phase jolt is a bit more clear. And with regards to amplitude, like percent signal change similarity is closer to the magnitude image, at least in this voxel. But it's the other way around. So when the finger tapping is happening, magnitude fMRI signal goes high, whereas phase jolt, and also in here, phase Laplacian goes down. So, okay, let's keep it in mind and have a look at.
Faruk, can I
Yeah.
ask something really quick? I mean, maybe you're probably going to get to this in the next slide, but I'm just curious if this somehow relates to the fact that the Laplacian is kind of over a larger area, and therefore you're seeing differences in essentially the segmentation. So like the difference between the gray matter voxel that you choose or the CSF voxel that you choose and the tissues that are next to it are getting closer together or farther apart.
Yeah, I will come to this actually.
Okay, great.
mean, just to clarify, there is no segmentation here. Like I didn't like separate gray matter or white matter. I think Tyler is highlighting that this voxel that I pick is just at a border that is between, let's say, a large vein and gray matter. And maybe during the activity and rest, like they are moving a little bit, and this is somehow propagating to the phase measurements.
Yeah, that's
did
right.
I summarize correctly? Yeah.
Actually, just following up on that, does it matter also that the kernels, I thought you were asking about the kernels of the second derivative are much larger, actually, right? Because by the time you're doing second derivative, you're kind of walking out to two neighbors out. So it's
Exactly.
kind of 5, 5.
Yeah. I mean, so just I didn't talk about it indeed, but like here I am using the smallest kernel that is basically one jump neighborhood or face-to-face neighborhood of voxels. So it's basically like to compute the first derivative you consider, and this is computed in 2D because this is anisotropic acquisition. You just consider 4 other voxels. And of course, like to go to the second spatial derivative in those neighboring voxels, you compute it again. So indeed, like once you are moving to spatial derivatives, you are integrating information from a larger region. So you are kind of losing a little bit your spatial accuracy, I guess. But also, like we discussed this a month ago with, and Ravi was saying that I mean, at the end of the day, when you pre-process the MRI data, like motion correction, resampling, and so forth, you induce spatial smoothing anyway. So I think if you keep your kernel to the minimum when you compute the spatial derivatives, this is not the biggest concern. Like, but indeed, it's a true statement that when you compute spatial derivatives, you are integrating more information from neighboring voxels. So let's show some statistics results. And here, this is why I like this data set so much, because it's just finger tapping, gradient echo bolt, and after minimal pre-processing, I'm looking at the T statistics, that is the contrast between finger tapping versus rest conditions, and you see it's like exploding, basically. Like it's everything is there, like bam. Gray matter is there, like all the like veins and so forth. Of course, you don't see underneath, but I'm familiar with this data set. And here, especially specifically for Paul Taylor, I plotted the unthresholded maps as well, putting the gray matter boundaries. And you can see that there is no doubt that like there is activity that correlates with the task, and you can detect it very easily with magnitude gradient echo bolt imaging. Now, let's compute the phase Laplacian and do the same. Well, this is FDR thresholding, by the way. So you can zoom in and look at the values, but they are in a similar T statistics range. Well, you definitely end up seeing some activity in the phased Laplacian. Like that's undeniable. There's something is there. When you look at the unthresholded data, yeah, it is there as well. There is like maybe this strange thing going on that one side of this activity is blue, other side is red, right? It's not like at one direction. When you look at the phase jolt, it is maybe a bit simpler because the activity is in the same direction, that is the opposite direction of the magnitude gradient echo bolt. And of course, the spatial extent is much smaller. So like, what's going on? How can we understand these differences? Like, but one takeaway from all this stuff is that there is definitely brain activity to be detected in the spatial derivatives of phase. Like this, I think we cannot deny that statement. And to convince you even further, I have a bunch of data sets. Now I will show you just a couple of ones that I had time to process last week. So here, for instance, I'm looking at a totally different data set from a different lab, courtesy of Logan Dowdell, 1.6 millimeter isotropic at 7 Tesla, quite fast TR, 650 millisecond, 2D EPI. This from CMRR, from our friends at Minneapolis. And you can see that the resulting maps plotted in the same way, again, T contrast between the visual stimulus versus rest here. The magnitude image bold maps pop out quite a bit in the occipital cortex. I had to plot them in the sideways to make them fit in a larger way in the screen. So this is like the frontal lobe, this is the occipital lobe. And definitely, again, like when we compute just very straightforward, the phase Laplacian and phase jolt, there is activity that survives the FDR threshold. So there is definitely something there. Again, undeniable. And this last data set that I will show is the same experiment, same stimulation, but acquired at sub-millimeter resolution, 0.8 millimeter isotropic with a longer TR. And again, there is activity that survives. I believe it's, again, undeniable that when you compute the spatial phase derivatives, there is something there. Okay, so what is it? What's going on? How can we understand this thing? Well, luckily, there are some really nice papers that I have reached going back in time and following the literature traces. On the left side, okay, first I will look at the left side. I am showing you the data from Renzo after pre-processing, I believe here. And look at the center of the data. Like, what do you see there? Just in case if you maybe didn't see the time series in this way in the past. Well, it is going like this: black becomes white, black becomes white, right? Like, so that is basically the effect of the finger tapping. When it is more black, it means that there is more deoxygenated blood there, so the signal is lower. And when there is task finger tapping, the oxygenated like oxygenation level increases, And this is a very large vein. I can also tell you based on the anatomy and knowing the other slices. And in the oxygenated level, the signal, of course, goes up, as we expect from like standard fMRI, right? And you don't need to do any statistics, nothing. You see this like periodic activity going up, down, up, down. So, okay, what's going on and how can we understand this whole thing? That's basically like fundamental fMRI thing. The best explanation I came across so far associates this with the phase is from Hogenrad, that actually Ravi Menon references this in his 2002 paper about phase regression. You can, okay, let's have a look at the image. So we have rest and activity. On the left side, we have magnitude. This is an fMRI, like an image that is acquired at 0.95 Tesla, right? 0.4 by 0.4 by 3 millimeter isotope. This is pretty nice, actually, in terms of resolution and finger tapping experiment. So in the rest, you have this black ring around, and this is a large pile vein that they detected, and they positioned their fMRI acquisition on top of it to be perpendicular to it. And in the activity, you see that the difference of contrast between the vein and the surrounding tissue decreases because oxygenation increased, and we end up having more similar tissue contrast. Things are more like become on resonance. When we look at the phase of the same data, you can see that in the rest, there is this large phase difference between the surrounding tissue and the large pile vein. And that difference, again, also decreases with activity. So more oxygenation there is, the signal in the pile veins become less different than the surrounding gray matter tissue. Like that's the story that's going on. And you can detect this both in magnitude and the phase components of your fMRI signal. And indeed, like this argument in itself tells you that by theory, you should definitely see like brain activity in just looking at the phase, or even like spatial derivatives of it, because there's this contrast thing going on, right? Like if phase was staying exactly the same between rest and activity and just magnitude was changing, of course, then there would be no reason to expect to detect any like stimulus related brain activity in the phase, but it is not the case. There's a coupling between, in other words, magnitude and the phase signals. So now here I will switch to something a bit more practical and interactive. Okay, so just to give you some further idea. So now imagine a single voxel that we recorded. Looking at a single voxel, what you see in black line is the so at this point there is the complex valued voxel. So we have one real number recorded, one imaginary number after Fourier transform. So voxel is represented by two numbers. What we look at by default is we look at the magnitude of that voxel. That's our like traditional magnitude fMRI time series. So there is this whole like modeling behind it, and it goes back to this Hogenrad and Menon papers from 2000 and 1998. It means that this, let's say that we are looking at a gray matter voxel. The theory, and I'm like summarizing a couple of papers here, and I hope it's fine because I didn't prepare to give like a full reference list about this yet. It's just like a work in progress. So basically, there's this thing called dual component model of the fMRI signal. So what it means is that we have these two components that makes up the black vector. It's just like two vectors added on top of each other, like vector addition, like simple geometric stuff, not even MRI physics at this point. And the gray part is some call it the gray matter signal, others call it extravascular signal. Hopefully, like these terms make some sense to you. And in red, I plot the intravascular signal or the blood part of the signal. And just to show you around, if you have more blood in your voxel or intravascular signal in your voxel, this red vector will grow. And hopefully you can see that this goes to partial volume and a bit like to the direction of what Tyler was mentioning. So the amount of different type of tissue in your voxel has an effect on the signal that you measure by itself, both on the magnitude and also the phase of the signal. Like if I just increase and decrease in a drastic way the red component, I hope that you can see geometrically that not only the length of the black line increases, but also the angle of it changes a little bit, right? So the phase, measured phase changes. And here on the below, I am trying to plot or just make it a bit more clear by plotting the magnitude and phase components to see that like the fluctuations here relate to the fluctuations there to show you the coupling between them. Okay, and like there are other things that are going on, not only like these two things in length can change, but the angle between them can change. And oops, not this parameter, is delta. So okay, so just in an exaggerated way, I am almost like making a comical situation here. So let's say that this is deoxygenated blood, okay? And basically the theory says that and also this is Ogawa saying it in like 90, when the blood becomes more oxygenated, this intravascular component becomes more parallel to the gray component, right? So this is, let's say, activity, oxygenated blood. This is deoxygenated. Length, hopefully you see it here, not only the length of your black vector changes, but the phase of it also changes, right? And phase, I mean just like the degree here. There's a question, Nadia?
Yes, thank you so much. I wanted to ask a question with respect to what you're talking about. You're really describing this relationship, assuming that the artery, venules, and veins have a normal connection. What if you had a patient who had an arteriovenous malformation where there's a shunt? To what extent might that impact where the magnitude and or the
Yeah,
phase?
thanks. I got the question,
Yeah.
but this is outside of the scope. Like
Yeah.
this is not my theory or anything. I'm
Okay,
just
okay.
summarizing what is talked about in the literature.
Yes,
Maybe
but
we can
I just
circle.
want to say that this is assuming that there's a normal anatomic distribution.
I guess so. Yeah. Yes. Yeah. I believe that's true. Yes. Thank you. So okay, like deoxygenated, oxygenated, and hopefully you see this geometric relationship. So now another part of this story, this geometric story, is the following thing. Oops. So what if we have very little gray and a lot of red vector? That is like heavily pile vein dominated voxel. So now when the deoxygenation changes, like let's say 90 degrees, like the same amount as it was changing previously. So the resulting phase changes in the black vector is like really large. However, now imagine the opposite situation where you have a lot of gray and little red, okay? Now let's induce the same 90-degree change in the difference between oxygen, like the blood and the gray matter voxel. Well, like as a result, the phase that you can measure, that is the difference, this degree of this red, like black vector, doesn't change as much, right? Like it's just changing a couple of degrees here. Whereas in the other way around, it changes massively. So that's the whole story, actually. Like this is why also Ravi Menon says that you can detect phase changes in macro vessels, like macroscopic veins mostly, very reliably because they are mostly made of blood, right? So any phase changes there, like becoming more oxygenated or less oxygenated, have like a very direct and large effect on the measured phase. But if you are in a gray matter voxel, that is partial volume in a different way, then actually like changes due to the oxygenation as measured from the phase of the measurement is not so high. So that's why also he pitches his method as like a macrovascular cleaning or macrovascular like regressing out method. So hopefully this made some sense or connections. So okay, I'm approaching towards the end. Let me check the time. So there's this other part of the story. This is a bit complicated story, but I think it can be improved with some educational material. So what's going on over space? Like, what's the story here? So, okay, just a very simple scenario. There's some neuronal activity here, very simply drawn here. There's a vein. I didn't draw arteries here. So it is like draining the oxygenated blood from there because there's activity more, and it reaches, it goes up in the vascular hierarchy. But there's another part of the story, and that is the B0 angular dependence of the vessels. And I know John is around here and he talks about it many times. So basically what you should imagine is this, like there's this pile vein up here. It by itself exerts a magnetic field distortion outside of itself, which I try to indicate here with this like distortion isodistant lines. So these are like distortions in the magnetic field or susceptibility changes, whatever you want to call it. And realize that the B0, like this pile vein here is perpendicular to B0, the main magnetic field. Okay, so which in a way like already makes us conclude that, oh, like there might be a neuronal activity here, but I might end up measuring some signal changes over there because like the oxygenation changes going higher up in the vascular hierarchy. And then at the end, it ends up like exerting a different extravascular distortion around the pile vein. So, and this is the whole story about BOLD being like non-local or not spatially specific. And that's like something that Vaso tries to address from an acquisition point of view. Like this thing, like your activity is here, but you will measure some fluctuations there, even if you disregard the pile vein. And this connects to Ogawa's 1990 paper that is done on rodents, I believe. Basically, this is the start of like fMRI as we know it. Between the oxygenated and deoxygenated conditions in a capillary here that is plotted in a gradient echo acquisition, you end up measuring this like large extravascular field change. And I hope you can see that the walls of the vein here is like there, but here there's a like a outside of the walls effect. And that effect is, as far as my knowledge goes, is nicely captured in this Boxerman's 1995 equation 1. That basically tells you how these magnetic field distortions behave inside or outside of the vein as a function of the angular difference of the vein with regards to the B0, the main magnetic field. Okay, so why am I talking about this, all this stuff? Well, we are trying to understand what's going on in the phase and like maybe also magnitude and phase, also in their spatial derivatives, right? So basically, like the magnetic field is changing, that is getting more or less distorted based on the oxygenation level. It has implications on the measured phase and magnitude. And now, in the context of this ISMRM abstract and this whole discussion about phase spatial derivatives, now we need to think of these images, but not only them, but their spatial derivatives. But this is like quite complicated. So I try to tackle this problem by making another simulation that hopefully will give you some extra idea. Okay, on here you can see like a vein that is perpendicular to the main magnetic field, and here we are measuring the distortion of the magnetic field, like this delta B. And I can change the angular difference. So I can make the vein parallel to the main magnetic field. Then there is no extravascular distortions. It's like very homogeneous. There's only some like magnetic field change inside of the vein based on Boxerman 1995. Whether you agree with it or not, that's like another discussion. And as the angle increases, you see that the inside of the vein magnetic field distortions are changing, but also outside there is like a field that is being imposed. That's like the extravascular component. And of course, this whole thing depends on the size of the vein as well. Like this is a small vein inside of a voxel. You imagine this is a very large one. Don't worry about zeta for now. And what I'm plotting here is the Laplacian. This is a spatial derivative of this magnetic field distortions and the jolt, the L1 norm of the second spatial derivative. And hopefully you can see that, look, I'm changing the B0 angle, and there is some change in Laplacian. You see, like there's this like crossing point. And these are very much a work in progress, by the way. I hope I coded everything correctly, but don't quote me on that in the future. This is like very much experimental right now. So, okay, what do we understand from it? Well, if you measure a change in Laplacian, it might come from, like if a vein is changing its orientation in a task versus rest, this, of course, like a nonsensical scenario, but this can yield Laplacian changes, okay? How else we can affect like a Laplacian that is measured in this, like, let's say, small square area? Well, I mean, that can also change a little bit with the radius changes. Like if the radius becomes smaller or larger, the amount of blue and red voxels there will increase or decrease in a given region. I mean, this whole thing is a given region, so you can see that like this has more blue and red voxels than this one, right? I hope you can see it. So if like radius of a vein is fluctuating between rest and task, this can like yield Laplacian changes as well. I don't know how plausible it is to think of it in this way or to this magnitude. Or there's this zeta parameter that basically kind of changes the shape of the external magnetic field. That I made it up, this parameter, so I'm not saying this is plausible or anything. But this is another way to kind of, maybe you can imagine there, like inducing Laplacian changes. Okay. So hopefully this gives
Sorry,
you
Faruk, can I just ask there, the Laplacian is highly, can I just say the Laplacian is highly localized. Is that because it's a linear changes, and so by the time you get to the second derivative, except for just that ring, it goes to 0 unless you change zeta. So your default zeta was assuming some kind of linear changes. So when you do the second derivative for Laplacian, everything is 0 except at the edge.
Yeah, zeta is basically like this guy that is square. I just put it as zeta. I made it up like just to change something in the extravascular space, like give like a different spatial feeling to like it is just there to demonstrate that how you can kind of measure phase Laplacian change. You know, what could be happening if you are measuring like a large fluctuations in the phase Laplacian. So I believe it can be due to like vein diameter changes, vein angle changes. That is, of course, less implausible to think that they are like veins are like dancing around in a task versus rest. Or there is like some field that is imposed that is like interacting differently, and then it results in a different like extravascular like a field in a like a from a shape or geometric point of view. Anyway, I actually don't know exactly what's going on. I'm just trying to think about it. But also there's another point with regards to the ISMRM abstract, like their echo times are very early. And everything I have kind of shown here, try to convince you that there is brain activity detected in the phase Laplacian and phase jolt. Like these are usual echo times of gradient echo bond, like 20, 30 milliseconds. Whereas in that ISMRM abstract, they have very short echo times. So I am suspecting that like if there is some effect that only happens in the very early echoes, I mean, if you take that ISMRM abstract, you have to think that something with regards to conductivity or electrical fields in the white matter is like somehow giving rise to a phase fluctuations to such a degree that you can detect them in the second spatial derivative of it. I wish actually they would have plotted the magnitude images there as well, and the results of it also, like the unthresholded images, so we could understand a bit better like what's going on or what could be going on in that ISMRM abstract. But anyway, this is already like a discussion. So I would like to end. This like a bit open-ended, like these things are going on, you know, I'm trying to find and think about what's going on, what is there. But there is one big takeaway that is kind of the conjunction of this conductivity ISMRM abstract and my like anatomical phase jolt imaging, and there is definitely brain activity that can be detected in the spatial phase derivatives. That's like justified by theory, justified in practice. It's like really there. So what is it? Is it conductivity changes? Is it like neuronal currents somehow? I don't think so right now, because every big change that I see in my phase data and also my collaborators, the data that I get from other people, is like all localized in large veins, and it makes complete sense. Like it's an oxygenation sensitive contrast, like derivative contrast, and you detect stuff there. Maybe like this echo time is really important. If you really need, if there's like really an effect that is somehow related to neuronal currents or whatever, like conductivity changes, I do not understand fully how it can be right now, but maybe then it's like a different story that requires different formalisms and so forth. So just to end on a practical note, actually just today, a couple of hours ago, I published a new Laney version. We will compile it for Linux and old Mac versions in the following hours with Renzo. And there are these bunch of new programs there, LN2 gradients, Gramag, and this like phase stuff, LN2 phase Laplacian, for instance. So I just want to show you for a second that if you right now have some phase data, and if you want to have a look at your phase Laplacian or phase jolt time series and like GLM results and whatnot, you can do by doing this following. So you download Laney. There is this, let's say, phase Laplacian program. There's the help menu, tells you how to use it. It's a command line program. And now I'm just going to give it a phase time series. Oops, I don't want to run it actually. And just to show you practically, so this is a real phase time series. You can see here. It was too fast. I meant this one. Oops. This one. So just to show you, so this is like fMRI time series data, and I have now computed the phase Laplacian. Took like a couple of seconds because it's a small data set, but in the bigger whole brain ones, it will take a couple of minutes. This didn't compute correctly, and this was on purpose because the initial data that comes from your scanners, if they are Siemens, is in the integer 13 range for some reason, but written as an integer 16 data precision. So you need to add this int 13 flag afterwards. And once you do that, it will compute correctly the circular difference, the second spatial derivative, and give you the following time series. And hopefully you can see that this is much more like homogeneous, in a way easier to understand, like for us humans. And here you can just take this data and apply the rest of your processing pipeline, like motion correct, do this, that, whatever. So to show you the phase jolt, you do the same, it computes.
Faruk, I'm curious, does it surprise you that it's so constant, the phase inside the brain, the phase jolt being so consistent?
Not at all. It doesn't surprise me at all, because look here. Like inside of the brain, the phase changes very in a low frequency, low spatial frequency. Like it changes mildly over space. Maybe I can stop the time series. Whereas outside,
are we seeing the equivalent of like a baseline change that goes in there? Because or do you not have that either, like a phase baseline?
What do you mean baseline?
Well, you have like EPI data, often the kind of baseline might move a little bit. You detrend it or
Oh
something.
yeah, I mean you see this like a wave effect that is kind of washing over. Yeah, I mean I think this is due to
That's
maybe
just what that
oil
is.
heating up or something. Maybe Renzo understands that artifact better.
We have a global phase correction at the beginning of the scan, so there's no frequency updating at those agent data for HDR. Yes, yeah, there's a phase, like a frequency increase over the scan.
Yeah. So for instance, this is a different data set, much more conventional, and you do not see that like a large, like washing over effect. Not like, and also the funny way, like maybe it answers your question somewhat. So this is like a Nordic compatible data set. So they have the noise scan at the end, which is actually useful to have. And you can see that when you don't have like signal from the brain, you see the actual like distribution of the wave, which is like completely uniform distribution, of course. But when you have the brain that is high signal, it kind of constrains the phase values that you can measure anyway, like thinking of the complex valued signal. Okay, then just the final words.
Hey, Faruk.
Yes. Who's
Can I? This is John.
hey.
Could I ask? Actually, can I make like a quick comment and a question? This is super
Yes.
cool. I guess my comment would be, yeah, as you know, people generally are shy about doing fMRI with phase because it's so vulnerable to kind of physiological noise, right? But I kind of like this idea of taking spatial derivatives, right? Because insofar as this noise is sort of, kind of spatially kind of smooth, I think that the derivatives can help to get rid of that. And it seems like this method is a lot like QSM, right? Where you're trying to kind of isolate, these susceptibility effects from vessels. So I like the idea. I think it can help get rid of, and I guess people take derivatives of these phase maps just to help with phase unwrapping, right? So there's some, I guess, precedent there. But I like this idea of the spatial derivatives. I guess the question I wanted to ask you was, I was talking to Daniel about this. I mean, so the connectivity, right? So they're looking at Laplacian because they're trying to relate the measurement to connectivity, right? And that was taken from kind of connectivity mapping studies. We're trying to measure, connectivity of these brain structures. What kind of data were they using, right? Because I thought it was, I just couldn't remember. I mean, I was asking Daniel, I thought it was like an SSMP type sequence, right?
BSSFP, yeah.
Was it? Yeah, okay. And so that's why the echo times are kind of super short. I mean, I guess, yeah, because here it makes sense that, I like, again, the phase jolt, right? Because you're taking second derivatives, both for Laplacian and the phase jolt. But in the phase jolt, you're taking the L1 norm, right? So that kind of accentuates, whichever direction has like the highest derivative, right? It's kind of like a nonlinear combination that sort of accentuates. So it's pretty cool. And that does make sense why you're seeing these bigger kind of effects. But the interpretability is, I guess if you're trying to measure connectivity, which is what they're trying to do, maybe the Laplacian is. Yeah.
Connectivity, you mean like literally like correlation between two boxes?
Conductivity, I'm sorry.
Conductivity. Okay, sorry, I was thinking connectivity.
Yeah, because it seems like, again, maybe you could relate, the phase jolt to conductivity, but it seems like, for them, and again, I'd love to understand like the sequence, as you said, maybe it's something about the short echo time, maybe it's something about it being BSSFP. But yeah, that was my question. I just couldn't remember what they did. And it wasn't exactly kind of grading echo with a long echo time, right? So
to measure velocity, we also try to eliminate susceptibility.
Yeah. Yeah, so to what extent, because I guess my, my other question would be, I guess you didn't see much, in the white matter. I mean,
No, yeah, I was hoping to see something in the white matter, but also I didn't have like a clear finger tapping experiment that I can see the white matter tracks. Like Renzo's data was just on the surface, and the other experiments were all visual stimulation.
Yeah.
Although, like even there, like I mean, they were not closing their eyes or anything, so they were still watching the thing. So maybe it didn't come out, but no, I didn't see anything on white matter. I was a bit bummed about it.
Yeah, it's funny. We were talking about like BSSP the other day, and it is really sensitive to like off resonance effects. Right? So maybe there's some, some idea there. Maybe there's something about, again, about their acquisition that's helping.
Yeah, I think whether it is something to do with conductivity or I don't know, maybe neuronal currents and so forth. Like I don't know about that part of the story. Like I don't understand how it can be like because from a geometric point of view, like what phase Laplacian means and how it can be interpreted. I do not see the relation fully, but maybe like if in early echo time due to electrical activity, there's like some wave characteristic changes around in the white matter, maybe phase Laplacian would pick up that as like a curvature changes, because Laplacian kind of measures the like the curvature of the region. So yeah, maybe something like that. But I also like, the point is that I do not fully see how you can measure something in the phase derivative and not in the magnitude. Like that would be very strange as well. Like, so that's why I was saying I wish they plotted their magnitude data.
Yeah. Yeah, no, I agree. But again, those responses were so remarkable, right? I mean, they're so fast.
And Faruk, speaking of the time courses, what were they looking like in the data you just showed us?
The time courses,
Yeah.
the data I showed you. Perfect, because I
showed some maps, but maybe I missed it. Sorry, it was the beginning.
I put it as an extra material.
Oh,
This will be a part of my OHBM poster, by the way. Like so like, for instance, here in one of the experiments, just FDR surviving bolt versus phase jolt voxels, and here are the event-rated average time courses. So you can see that, I mean, they are not exactly the same voxels. I did very quickly, but you can see that it's basically the opposite of the. I mean, that's also other thing. Like I would not see how this can be different based on Ogawa's and Ravi's and Hogenrod's explanations of how oxygenation level is picked up by the phase and like I don't see how this coupling would be different.
Yeah, it's a bold effect. It's a bold effect.
Yeah.
And it's some susceptibility change, so it has the same timing. It's just in the phase, not the magnitude. Yeah, no, I agree. I mean, and that's why, again, that's what's so interesting about, right? Because this is pretty clearly a blood oxygenation effect of some kind.
Yeah.
But again, their effect is so fast. So it seems like it must, it's implies or suggests that it's something other than like a vascular effect.
Yeah, somehow. And by the way, this is for instance, Ramsow's data, and you can see the CBV from SSSI Vaso as well. And like one might think that, oh, they are very similar. Maybe we can do phase jolt instead of Vaso, but like the voxels are totally different. And
yeah.
So not to like confuse two things.
And so how do you think the phase jolt compares to FQSM? I mean, it seems kind of similar, right?
Yeah, I mean, honestly, like one reason why I computed this, like went into this jolt stuff, because I was annoyed at the phase data preprocessing stuff. Like you need to unwrap it, you need to brain mask it, you need to background field removal, like, and all these steps, like I don't agree with some of them, even from like a problem point of like, why are you forcing the circular measurement that is phase to be like a real number? I mean, that's coming from minus infinity to plus infinity. Like it's a circular measurement. You need to treat it as such. You cannot like just force like regularity into it. Indeed, like it doesn't work. There will be singularities and so forth. Then you need to brain mask. Then if you want to look at the voxels that are at the edge of the brain, it's outside of your mask. Like I maybe just a bit spicy take, but I do not like FQSM stuff because of this like pre-processing point of view. And I think we can maybe just do away with like some of the things that they do and focus on the origin of the contrast and maybe like pull it up with derivatives, phase derivatives.
Okay, that's a good answer. Okay, cool. Thanks.
Can I make a comment?
I also see the Demiral asking a question. Jeff Dine is asking? Yeah. Yes.
So I just want to clear up a confusion. This abstract didn't look at an off-resonance effect. So Rafi last time and some people here today, they seem to be suggesting that this conductivity change causes an off-resonance effect. And that this is important to realize, because that means that the effect size doesn't scale with echo time. So if you're going to say, like, I didn't see anything in white matter at an echo time of 30 at 7 Tesla, you are 2 orders of magnitude more sensitive to bolt effects than they are, meaning also that your signal stability is going to be much less than what they have. So I think they had a 0.1 degree phase stability. I don't think you can ever get that in your bolt type of data. So I think you shouldn't be looking for Laplacian phase effects in both data to try to find conductivity changes related to fMRI.
Yeah, I mean, that's not what I'm doing. I was just showing the oxygenated related changes in the long echo time phase Laplacian. So I'm not trying to search or find their effects on the normal fMRI data. It's clear. I'm just saying that
you were saying you didn't see anything in white matter, but I mean that is just because your phase stability is not nearly as good as what they have, because they
yeah, sure. No, I
very
agree. I agree. And actually, like, my point was that, like, if we were to look for what they are suggesting to see, we need to have a very low echo time fMRI protocol to catch it. We cannot catch it with like long echo time. We can only catch big vein oxygenated base changes. Like that's my point. So we actually agree.
Okay. Yeah. Okay. Good.
Demiral.
Ömer, so I have quick 3 questions. How do we, from the Siemens machine up 3 Tesla, how do we extract the phase data that we can use your software, for instance? Second question is, how does the Philip angle and, you know, Ernst angle may influence the your phase derivatives? And the third question is, I am really interested in the brainstem nuclei, like superior collicus or ventral tegmental area, where there are a lot of like capillaries and you know, like main basilar arteries and things like that, which are really dominating around this pons and the brainstem regions that supposed to be close to the surface. So do you think your method can be used to eliminate any overlapping partial effects from those blood arterial effects on the cortex or the brainstem regions? Yeah, that's
Okay, yeah. Thanks for 3 questions. So first one, how to extract phase data from scanner. I think you just need to like change like one parameter to make it export magnitude and phase data. I don't remember which parameter was it in the console. Like
okay, so since we have the dicoms from the magnitude, we cannot reconstruct it now, right? We have to do it in the beginning.
Yeah, if you only have magnitude dicoms, it means that you like
Done.
your phase data into trash bin already. So
Right.
So, okay, the Philip angle, Ernst angle relationship with the phase measurements. Actually, I don't know what to say. Is there someone who can think of something? I didn't thought about it.
I was thinking it may, because
As
I
long as
think
it's
that
not overflipping. Yeah. I think if you don't do over 180 degree, it shouldn't matter for the kind of experiments like gradient echo EPI that Faruk is talking about. I think if you do kind of different sequences, and then you have different kind of simulated echoes across flip angles and all that stuff. I think first order you don't need to worry about flip angles.
Yeah, and the third question was, can we account for some vasculature effects, partial voluming in the brainstem subcortex regions, somehow combining phase and magnitude data? I think there the answer is yes, if I understand the question correctly, because then it's like a similar situation as Ravi plots. That is, you have the ability to detect like signal changes in the big veins, essentially using the phase data, and you can, in a way, since they only come up in the big veins, you can regress it out from your magnitude image and like clean it up a little bit. But practically, I don't know how useful it will be for the scales of the vessels that are at the brainstem and the areas of interest for you. So something to look for in practical. But it might work. Yeah.
Faruk, I have a question.
Yes.
Thanks for the great talk. There's no doubt about there is an activity-related changes in the in the phase. I mean, there are early studies on ICA running complex ICA using phase and what so on. But what they didn't show is like the derivatives you use is kind of different spatial patterns and activities. Like you showed 3 different activities. I was curious, like if you ever look at it if magnitude or like jolt is always subset of magnitude? Is it always adjacent to magnitude activation, or they're complementary? For example, you show in Laplacian there's like positive and negative side by side. Do you see those features in visual cortex only, or is it in brain area related? Like, is there a spatial relation in between those?
Yeah, I believe definitely there is a special relation. For instance, here, I mean, if you agree with the fact that in this long echo times, you detect oxygenation changes in the phase and phase spatial derivatives, it basically implies that it has to be at least a subset of the magnitude activity changes, because they are like tightly coupled. That's what Ogawa argues. That's what bold fMRI is built upon. But this phase thing comes up quite clearly when you have a large intravascular component in your signal. So like that's why it kind of pops up, and this is definitely a macro vein, like pile large vein. I know from the data. Of course, it spreads around a little bit, and you can use this to regress out from that data, so it will be like a bit more clean over there. But it's not like you get rid of your all of a sudden like oxygenation effects in your gray matter. Like for instance, more Vaso thinking, it tries to kill the signal from the arterial blood from like acquisition point of view. So like you in here, and also this is in line with Ravi's methods and his papers, you kind of mitigate the large pile vein effects.
Yeah. But the one you show on the visual was kind of adjacent, right? In this case, it's kind of
this one?
Yeah, I think there are non-overlapping regions there too. That's what I'm trying to say.
I feel like I see sometimes, yes, but this has to be looked into more carefully with like a more varied data sets and so forth. So I could be maybe. I don't see exactly how it could be in these long echo times, but maybe, yeah.
Yeah, I asked this question because like in the beginning of your talk, you were showing some anatomical images that is kind of working as like edging, like edge. It just emphasizes the edges more. So if any derivative could see like in time series, if it work like that, I'm not sure about that. Just
there one has to distinguish between like this phase derivative giving a high response on a tissue boundary, like becoming high, versus its like fluctuations over time, assuming no head motion and so forth. Like when you, for instance, like Z-score voxel-wise among time series, then the image would look much more homogeneous. So like one should not confuse the edge popping up effects with like time series fluctuations.
Yep. Thanks.
Anything else? So I will be at OHPM. I have 3 posters there. 2 of them are from ISMRM, and 1 of them is focusing on fMRI phase jolt. And I will have some related project in the OHPM brain hack. So if any of you are going there, you can find me around in Seoul, hopefully.